All right, so I want to continue our discussion about finding three mutual friends or three mutual strangers at a party. The theorem that we discussed had the hypothesis of at least six people at the party, and so I asked, well, what about if there were only five people? And so what I'm drawing right now is an example of a coloring of the K5 graph that has a coloring using two colors that has no red triangle nor no green triangle. So this would correspond to no triangle of friends or triangle of non-friends. Okay, so K6 is the sort of lowest or the smallest complete graph that is forced to have a triangle in a two coloring. So this is the statement of the theorem sort of in graph theory terms about the friends at a party. So the statement is that any complete graph on more than six or more vertices whose edges are colored with two colors must have a triangle of one color. So let's go ahead and fix a vertex at random. I know that the degree of that vertex must be greater or equal to 5 because there are at least 5 other vertices in the graph. And because of the pigeonhole principle, at least 3 of those must be colored the same color, right? There are only 2 colors and there are 5 edges there. Okay, so let's suppose that at least three of the edges are colored with the color blue. So I'll just draw this on the picture over here so I get a visual. But it doesn't matter whether this is like 4 blue edges and 1 red edge or something, or all of them are blue. All I'm saying is there are at least 3 that are one color. So let's suppose that these 3 are colored blue. Let's focus our attention on the vertices at the other end of those blue edges, and we'll just consider all the possible colorings of the edges that connect those 3. So I'm going to draw some 3 edges here to represent those things, and let's consider case number 1. Suppose that all 3 of those edges are colored the same color, regardless of whether that's blue or red. Well, then obviously, if they're all colored the same, we've found ourselves a triangle, right? Ignoring the blue edges entirely, the edges that connect these 3 vertices are a single colored triangle. Okay, so that's obviously just one specific case number 1. So for example, there could be 2 different colors used instead of all 3 being the same color. Say is if 2 colors are used in these 3 edges, at least one of those edges has to be blue because the only 2 colors I'm using are blue and red. So with that, I can focus my attention on the blue edge, whichever one of those 3 it is, and it's going to form a triangle with the 2 of the blue edges that I drew originally. And so there is my same colored triangle. All right, so now let's move on to the Coningsburgh Bridge problem. This is a famous problem posed by Euler, and it basically goes like this. You want to walk around the city of Coningsburgh, visiting each of the land masses, and also traversing each of the bridges exactly once. And you want to start and end at the same place. So I'm just going to scribble for a little bit and try and do this. Nope, I failed on that one. Let me try again. I'll start on C, cross some bridges, got back to C. Oops, I didn't get that last bridge. Try again. And you should try as well, because it's fun to sort of see what's going on with the problem. And so anyway, so Euler said, can this be done? Why or why not? Let's rephrase it as a graph theory problem. So I'm going to write a dot for each of the land masses, or a vertex for each of the land masses, and then the connections, the edges, are going to represent bridges between those land masses. So this is not a simple graph anymore, but anyway, it is a structure that represents the whole bridge situation for Coningsburgh. So I'm looking for some way to walk around this graph, so traversing the edges of this graph from vertex to vertex in such a way that I start and end at the same vertex and I cross each of the edges exactly once. So such a walk, let's say, is going to be called an Eulerian circuit. I'm just copying all the different definitions from the book, and I want to focus on circuits, basically. So that's the second to last definition there. A circuit, a closed walk that visits all of the edges. So let me just, introduce some other important definitions for this topic, and that's the notion of connected and connected components. Connected graph is a very intuitive thing. It basically says the graph comes in one piece. So like if you can walk from one vertex to another, regardless of the pair of vertices that you start with, you call the graph connected. But if there aren't enough edges to get from some specified pair of vertices, then the graph will be disconnected. Be careful. This kind of notion is independent of drawing the graph. So like, even though I visualize this graph as being one piece, that crossing right there isn't like it's not a vertex in the graph. So when I redraw the graph, I realize, oh yeah, okay, this graph is not connected. Another useful definition for the discussion is that of a subgraph. So we call H a subgraph of G if it's basically any subcollection of the vertices and edges. So I'm just gonna like sketch, by way of example here, some different subgraphs of the complete graph on 5 vertices G. These are all just some selection of vertices and edges from the original graph. Okay, now let me introduce the notion of connected components now that I have the notions of connected and subgraphs. So if you look at any G, it might be connected, it might not be connected. The connected components are the so-called maximal subgraphs. So they're like the chunks of G that are connected. So again, by way of example, let me show you what I mean by this. If I start with a complete graph, in fact, all complete graphs are connected, there's only one connected component. This graph that I'm drawing here is not connected, and we can see two connected components, the triangle and the isolated vertex. Those are not only connected subgraphs, but they are maximal. Here I'm identifying this V subgraph of G that is not considered a connected component. Even though it's connected, it's not maximal because that other third edge is not included. All right, so now let's see what we can say about the existence of Eulerian circuits based on the degree of the vertices in a specified graph. So theorem 10.1.2 says that if you have an Eulerian circuit, then it must be the case that every vertex has even degree. And we may have noticed from the Coningsburgh setup that odd degree vertices were sort of causing problems. So suppose that your graph does have an Eulerian circuit and fix a vertex randomly. I want to argue that V must have even degree. Well, here's the point. If your circuit is to truly be an Eulerian circuit, then every time it enters a vertex, it needs to exit. Even if that's the original vertex where you start. Every single time you exit the vertex along an edge, you have to enter along another edge. So that means all of the exit edges are in one-to-one correspondence with all of the entrance edges in any given vertex. That makes the number of edges attached at a vertex even. So that's sort of how the proof goes. All right, well, back to Coningsburgh now. Here's the graph that represents the city with its bridges. The contrapositive of the theorem that we just proved says that, the fact that we have even one odd vertex here means that there's not going to be an Eulerian circuit. In fact, all the vertices have odd degree here, so that's a bad situation if you're looking for Eulerian circuits. Okay, now here is the converse of, well, converse formulation of the theorem that we just proved. This tells you when you will have an Eulerian circuit. So if you have a connected graph, and certainly your graph would have to be connected in order to have a circuit. If you have a connected graph and every vertex has an even degree, then you're guaranteed to have an Eulerian circuit. We're going to focus on constructing Eulerian circuits in a graph that has them. So the book presents an algorithm, and I'm presenting a different algorithm called Fleury's algorithm. Sorry about the misspelling there. And the short way to remember Fleury's algorithm is don't burn bridges. So let me tell you what a bridge in a graph is. A bridge is an edge that when you erase it, it disconnects the graph. Okay, so let's take a look at some examples so you get an idea of what a bridge is. So let me make some drawings here and identify the bridges and the non-bridges. So in this graph right here, you can see that these edges here to the right are bridges, because if I were to erase any one of them, they would split the graph into two pieces. These edges that are involved in the triangle are not bridges, because when you erase them, they do not split the graph up. Now let me show you how the algorithm plays out and in a connected graph that has vertices of all even degree, so that I can show you, how to construct an Eulerian circuit. So this isn't the only algorithm. Again, the book presents a different one, but this I thought for an alternative I would show you how this goes. So as I said before, the way you think of the algorithm is don't burn bridges. That's the shorthand. Now let me lay out this as sort of a step-by-step procedure. So start at a vertex at random. It's got an even degree, and all the rest of the vertices have even degree, and you're basically going to just pick an edge and traverse it. Now there's a little bit of rule that you have to follow in that selection. If the only edges attached to that vertex are bridges, then you're forced to select a bridge, but otherwise choose a non-bridge edge. And that's a rule that you're going to keep in mind as you build your circuit. So you start at a random vertex, find an edge attached to it that's not a bridge if you can, and sort of imagine walking across from that vertex to the vertex that's at the other end of that edge, and then you're going to erase the edge. Now it's fine if that edge was actually a bridge and you're forced to select it, erase that edge as well, and in the case that it isolates the vertex that you started at, you can erase that vertex as well. Now you're at a new vertex and you rinse and repeat. So take a look at the edges attached. If you can find any non-bridge, traverse it and erase it. If you're forced to select a bridge, then cross that bridge and burn it. And in the case that it isolates the vertex that you started at, then erase that one too. Okay, so this seems a little bit abstract. Obviously, it's going to make more sense if we run through an example. So let's do that now. All right, so I'm going to draw a connected graph that has each of its vertices with even degree. If I fail to have any of those qualities, then there's not gonna be an Eulerian circuit. So I do want to start with something where there actually will be one. And I'm going to follow the procedure that I just outlined, and I'm going to make a record of the bridges the edges as I cross them, and that's going to be my Eulerian circuit. So I'm just starting at this red vertex over here to the right, and I'm choosing the non-bridge G as my first crossing, and that makes me arrive at this next vertex. I'm going to choose the non-bridge I to cross there. And now at this vertex right here, I'm forced to cross a bridge. Now that's fine. I'll erase the bridge and notice that that vertex is now isolated. So I erased it as well. I'm standing at this vertex and I'm going to be forced to cross the bridge K. That's fine. I'll erase it along with the vertex and record that I crossed it. And here I am now forced to cross another bridge at H. I'll record that. And now I'm at a vertex that has some non-bridge options. I'll just select C to cross. That's one non-bridge. E is a bridge. I didn't choose that one, notice. Now I'm forced to cross a bridge. B, I'll record that. Another bridge A. And then D, E, F is how the rest of the Eulerian circuit plays out. Let me go ahead and sort of reconstruct the graph and show you what the Eulerian circuit looks like that I've just constructed using this algorithm. I've also got the drawing going at twice speed, so that might have been a little bit difficult to follow, but I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this sequence of numbers shows you the order of the bridges that I crossed to construct the Eulerian circuit.